Chapter 18. We got all the tools assembled. Required to analyze in detail any water solution so as to be able to calculate correctly the molarity of any and all species in the solution whose existence depends on pH, as most species in water solutions do. The tools. K considerations. We know how to write PSIs. We know how to write the equations for the principal Bronsted-Lowry acid-base equilibria which exist in such solutions. And on occasion, what have we discovered? Sometimes from the equation or equations which we write for the principal Bronsted-Lowry acid-base equilibria and the corresponding equilibrium constant expressions, we have more unknowns that we can evaluate based on the number of equations which we have been able to write. So in such cases, what do we have to do? What? What else? Material balance and charge balance. And with those tools, we can do what we said. Take apart any solution in nth detail to get again at the molarities of all species whose existences depend on pH. So to wrap up chapter 18, I've written 10th molar to 2 sig figs sodium hydrogen carbonate solution, 10th molar to 2 sig figs ammonium cyanide solution, two solutions which we have already considered. And now we'll look at them from a hydronium ion concentration determination standpoint. An ammonium hydrogen carbonate solution, which we have considered in brief, so as to recognize this solution is mildly acidic, mildly basic, or neutral. What is it? Mildly acidic. Mildly basic. Why is it mildly basic, this solution? Strongest acid in this solution is ammonium ion Ka 5.6 times 10 to the minus 10. The strongest base in this system is hydrogen carbonate ion. Kb value is 2.4 times 10 to the minus 8. I expect you not to remember that, but you certainly know how to get it. So the Kb value for the basic species exceeds that of the Ka value for the acidic species by a considerable amount, which dictates that this solution will be mildly basic. Now, the remaining question is, for this hydronium ion molarity computation that we wish to do for these solutions, do we need to consider material balance and charge balance? Directive or statement? If you consider material balance and charge balance and do the arithmetic properly, you're guaranteed to get the right answer. But clearly, if we employ material balance and charge balance in addition to the equilibrium reactions, we're going to do more work. So what's at issue here is, do we need to do the more work? Let's find out. And after we wrestle with these, one remaining and final consideration for chapter 18 is, how do we get at the hydronium ion concentration, correctly so, for a very dilute solution of a weak acid or base, where the ability of the species, the solute species in question, the weak acid or the weak base, is governed by equilibrium control? We'll finish with that one. What did we do last time with the with the sodium hydrogen carbonate solution? Well, we recognized that this is the main acid-base equilibrium reaction in the system because it involves the strongest acid in high concentration, hydrogen carbonate ion, with itself because it's also the strongest base in high concentration in the system. Now, if we wish to get a handle on extent for this reaction, we got to calculate the K value. So we'll write the equilibrium constant expression. Recognize that this is not an equilibrium constant expression for which we have the Ka made available to us. So as we began to learn about in Chapter 19, which will extend tomorrow in discussion class gathering, by application of Hess's law, we'll calculate the K value for this equilibrium reaction. That's very easily achieved because on multiplying this equilibrium constant expression for this equilibrium reaction and multiplying it by the one factor of hydronium ion molarity divided by hydronium ion molarity, what we recognize is that this equilibrium expression is a composite of Ka for hydrogen carbonate ion divided by Ka1 for hydrated CO2. Do you see that? Bicarb ion denominator, hydronium ion carbonate ion. There's Ka for hydrogen carbonate ion. What are the remaining terms? We'll check the terms so far considered just to assist us with the bookkeeping process. Quote unquote H2CO3 up top, divided by the molarity of the remaining bicarb molarity, because I lined out the squared and converted it to first power, times hydronium ion. That's 1 over Ka1 for, as we stated, hydrated CO2, or call it quote unquote H2CO3. So we put in the numbers, get the value for the equilibrium constant, 1.1 times 10 to minus 4. Now then, this reaction in and of itself does not allow us to get a handle on pH. We got to look at this reaction, which corresponds to Ka for hydrogen carbonate ion. Ka for hydrogen carbonate ion, 4.8 times 10 to minus 11, which of course was part of this K value evaluation process. Or the reaction which shows hydrogen carbonate ion reacting with water to behave as a Bronsted base. Kb 2.4 times 10 to minus 8. Can I use either of these reactions to get a handle on system pH? Can I use either of those reactions to get a handle on system pH? You're damn right. They each contain the principal species in the system that has acid-base properties, that's hydrogen carbonate ion, and they each give us a direct handle on pH. Because this reaction makes hydronium ion and this reaction makes hydroxide ion. Hey, the molarity value for each of which you know when you have pH. Okay? Now then, back to the question. For this system, to correctly calculate hydronium ion concentration, do we or do we not need to employ material balance and charge balance? Now, before you answer that, I want to make a statement to you. Call it an admission, if you will. A confession. How about that? Because I told you, one of my personal great satisfactions of teaching this class is every time I go through it, I learn more stuff. So when I wrote these notes, I thought that for this system, you in fact had to employ material balance and charge balance. And so you see the analysis of this system, the 10th molar sodium hydrogen carbonate system, pursued in that fashion. That's in the notes. I trust you've looked at it. But lo and behold, I came to recognize, if you pay close attention to the significance of the equilibrium constants, which are part and parcel of this equilibrium system, you will realize, as I finally did, No, we don't need to pay attention to material balance and charge balance to calculate correctly the hydronium ion concentration for this system. That means the hydronium ion concentration calculation for this system is really pretty simple. Now, what property of these equilibrium constants am I referring to? The property specifically is magnitude. Look at the equilibrium constant values. They're all on the board. None of them are big numbers, are they? But let's make a comparison. Which of the equilibrium constants is by far the biggest? The reaction for bicarb with bicarb, the reaction with bicarb with water as an acid, or the reaction with bicarb with water as a base? Bicarb with bicarb is 1.1 times 10 to the minus 4. That's a hell of a lot bigger than 4.8 times 10 to the minus 11, and it's also a hell of a lot bigger than 2.4 times 10 to the minus 8. Now, what may we now fairly conclude from the bicarb-bicarb equilibrium reaction about the concentration of quote-unquote H2CO3 compared to the concentration of quote-unquote carbonate ion? What may we fairly conclude about the relative molarities of those two species?
Carbonate should be more than bicarb.
I heard a vote for carbonate should be more than bicarb. I don't know how carbonate could be more than bicarb because the K value is pretty small. So carbonate could hardly be more than bicarb. But bear in mind what I asked. How does the molarity of carbonate compare to that of hydrated CO2? Quote-unquote H2CO3. How do those molarities compare?
Essentially equal.
Are essentially equal. In fact, the two significant figures, they are equal. Why is that a fair conclusion?
Because the KAs and KBs involving the carbonate and the hydrated CO2
are very small comparatively speaking. Which means, even though the Ka reaction shows the contribution of carbonate ion, and the Kb reaction shows the contribution of H2CO3 to the system, do you think the contribution made to the system by this reaction of H2CO3 will be substantial? You think the concentration contribution made to the system for the carbonate ion molarity by this reaction will be substantial? No. Now that means that from this bicarb-bicarb reaction, we can write this. That seem fair? Oh! Wait a minute. There. Let's write this correctly. M sub I minus X quantity squared. Because I forgot we got bicarb reacting with bicarb in this reaction. Okay? Is this relationship difficult to solve?
No.
What are we going to do to begin to get at solving? How about a square root on each side? Will that simplify matters? You betcha. How does the square root of this number compare to 1.1 times 10 to the minus 4? Is it bigger or smaller than 1.1 times 10 to the minus 4?
Bigger.
It's bigger, isn't it? Because when you take a fraction of a fraction, the resulting value is smaller than the original fraction, isn't it? So, With this, we can solve for H2CO3 molarity as well as carbonate molarity if the considerations which we made are correct. Let's see what I got. I got there it is. 1.04 times 10 to minus 3. Now then, keep in mind when we do arithmetic on these systems, we're going to extend the numerical value of each calculation to one additional sig fig in order to guarantee that when we get to the end of the line and calculate the molarity that we're really interested in, and round it back to 2 sig figs, we'll have the correct value to 2 sig figs. This, I presume, you learned about when you learned about dealing with sig figs in 2045. Now, let's go to this equilibrium reaction since it's got hydronium ion in it straight away, because I want to get the hydronium ion molarity. So, all right. 4.8 times 10 to minus 11, which is hydronium ion molarity. That's what we're interested in. Times the carbonate molarity, which we have evaluated, over m sub I minus 1.04 times 10 to minus 3. Well, we got one unknown. So we'll get after we solve for the one unknown, which is hydronium ion molarity, (4.6 times 10 to minus 9). Which of course is a molarity less than 10 to minus 7, keeping with the fact that this solution was recognized before we did any arithmetic. We recognized this solution to be mildly basic. So we knew the hydronium ion molarity would be somewhat smaller than 10 to minus 7. And that is somewhat smaller than 10 to minus 7. Now then, what would you do to convince yourself that this solution that we just applied to this system to get the hydronium ion molarity is correct? What would you do? You'd proceed through analyzing the very same solution, but employ all the details. Employ material balance and charge balance. Because, as we said, if you employ material balance and charge balance in addition to the principal equilibria, you got to get the right answer. And guess what hydronium ion molarity you will obtain if you apply material balance and charge balance? That's what you'll get. Now, am I going to write that one on the board? No, because it's in the notes. You already got that one. So that analysis has been done for you. But I suggest, for your own benefit, you work through this system, applying material balance and charge balance in addition to the equilibrium reaction considerations, just for your own benefit, for your own practice. And convince yourself you get the very same hydronium ion molarity. And so, after doing such, you'll realize when this main acid-base equilibrium reaction produces molarities of products which are far in excess of these same products produced by the other equilibrium reactions in the system, That's what we started by recognizing. That first equilibrium reaction, the one between the main acid in the system and the main base in the system, will give you equal molarities for the products. That's all we did. Now, if you don't get equal molarities for the products, then what we have done here in terms of method of solution won't be correct. But it is for this case. Again, the detailed material balance included, charge balance included analysis is in the notes. Take a look at it. Let's take a look at the second system, the ammonium cyanide system. And see if, for the ammonium cyanide system, if we wish to calculate the hydronium ion concentration, as we did now for the sodium hydrogen carbonate system, do we or do we not need to use material balance and charge balance? And we call that 2, I think. So, even though we've done this previously, let's rewrite the equation for the principal Bronsted-Lowry acid-base equilibrium in the ammonium cyanide system. Strongest acid is ammonium ion, strongest base is cyanide ion, so it's got to involve the ammonium ion, strongest acid reacting with cyanide ion, the strongest base. Wait a minute. To give us these species. And in fact, you can recognize, after we calculate K for this, we did the K for this previously. Let's do it again. Required trick to get K, hydronium ion molarity over hydronium ion molarity. Question. Could we just as well have evaluated K for this system by multiplying by hydroxide ion molarity divided by hydroxide ion molarity? Yes. You betcha. Because then we would have used Kb cyanide and Kb ammonia. But now we're going to resort to using Ka ammonium ion and Ka HCN. Ammonium ion, denominator. Ammonia molarity, numerator. Hydronium ion molarity, numerator. Ka ammonium ion. Up top, numerator, HCN, which means we're considering this as a product. So the HCN ionization equilibrium we're looking at is cyanide ion plus hydronium ion, double arrows, HCN plus water. And by now you recognize that's 1 over Ka for HCN, just like up here where we had 1 over Ka1 for H2CO3. All right, get out the acid-base table. (5.6 times 10 to the minus 10 divided by 6.2 times 10 to the minus 10 equals 0.90. That's a rather substantial K value. So let's retreat to a question before we proceed, which you know I would ask you. About a system like this. My girdle's falling apart, please remind me. If, at this stage of the game, I asked you to write the correct PSI for this 10th molar ammonium cyanide solution, what would you write? The correct PSI for the 10th molar ammonium cyanide solution, what would you write? Well, you'd write water. And you'd write ammonium ion and cyanide ion. Anything else? Water? I gave you that. What else? Would you write HCN? Would you write ammonia? Do you see this K value of 0.9? Do you think this goes to an appreciable extent before the establishment of equilibrium, this reaction between ammonium ion and cyanide ion? You're damn right. You got to let that K value talk to you. So if you're going to write the correct, complete PSI for this system, ammonium ion, cyanide ion, HCN, ammonia, and of course water. Would you then, if you had this system contained in a reagent bottle in the laboratory, would you take the cap off this reagent bottle, inhale? I hope not. Because the ammonia, with its acrid odor, would cause you to experience an unfortunate reaction. But in addition to that, you'd be sucking in a good quantity of gas chamber gas. HCN. You don't want to do that, do you? And worse yet, if you were to take a taste of this solution, because the active ingredient in HCN is cyanide ion. That's what does us in. We'll talk about this when we get to chapter 24. About how cyanide ion makes a stronger bond to hemoglobin. You know about hemoglobin? Than oxygen. Ha-ha! So hemoglobin no longer is capable of functioning as an oxygen transport system. Instead, now it's a cyanide ion transport system. We can't thrive on that. So down we go. So if you work, simply put, with cyanide-containing solutions, be careful. Now then, back to the issue of do we or do we not need to apply material balance and charge balance to correctly get the hydronium ion molarity for this system? Well, tell me. Could you go after hydronium ion molarity for this system by using Ka ammonium ion? Is that not a principal species in the system? It is. So can we use Ka ammonium ion? Yes or no? Yes. Damn right. Could we use KaHCN? Is that not a principal species in this system? Have we not just recognized such? Yes. So could we use that? Yes. Damn right. Could we use Kb ammonia? Damn right. Could we use Kb cyanide ion? Damn right. We're just letting this PSI stuff talk to us. You can use any one of those. But now let's pay attention to Ka ammonium ion. 5.6 times 10 to the minus 10. How does the magnitude of 5.6 times 10 to the minus 10 compare to this number? How does the magnitude of KaHCN compare to the magnitude of this number? Now Kb ammonia is 1.8 times 10 to the minus 5. That's a lot bigger equilibrium constant value than either Ka ammonium ion or KaHCN. So after having recognized that ammonia is also a principal species in this system, we can see that the reaction of ammonia with water to produce hydroxide ion is far more extensive than the reaction of ammonium ion with water to make hydronium ion, or that of HCN with water to make hydronium ion. But how does Kb ammonia compare to the equilibrium constant for this reaction? Pretty daggone small. Now how about Kb cyanide ion? Well, before we focus on the exact value for Kb cyanide ion, tell me, will Kb cyanide ion be a little bit bigger or a little bit smaller than this number? Smaller. I heard bigger and smaller. Both can't be right. Smaller, because Ka8Cn is a little bigger than Ka ammonium ion, isn't it? This is a stronger acid than this. That means the conjugate base of this, which is cyanide ion, is a weaker base species than the conjugate base of this. So out of my magic hat, I will pull up Kb cyanide ion, because I've only done this arithmetic 1,000 times, maybe more, and recognize that these Ka, Kb values are all very tiny. Next to K for the main acid-base equilibrium reaction in this system, what does that mean? What conclusion may we now fairly reach about the relative molarities of HCN and ammonia?
Essentially the same.
What about the relative molarities of ammonium ion and cyanide ion? What?
Essentially the same.
Essentially the same. How about that? So just like we operated on that system, we can now calculate the molarity of each one of these species from this. And here again we're faced with this really tough arithmetic. And so at this point, I mean after we complete this calculation, we know the molarities of HCN, of cyanide ion, of ammonia and ammonium ion. And so you could use any one of those K values to calculate pH for the system. Is this correct? You bet it is. Because just like the sodium hydrogen carbonate system, the main acid-base equilibrium reaction in this system has a K value that far exceeds the K value for any of these other reactions, which give us focus on hydronium ion molarity. Upshot, as we've already said, the molarity of this equals the molarity of this, and the molarity of this equals the molarity of this. You do the arithmetic. All you got to do is copycat what we did here, just with different species. Now then, just for comparison as necessary, we'll leave that on the board. And we'll go to this. System small Roman 3. Right now on your paper, write the equation for the principal bronze-silver acid-base equilibrium reaction in this. Come on, let's get going. For those of you who do this successfully, you can have another sample of the residual Valentine treat. By now, really, writing these equations for principal acid-base equilibrium reactions in systems such as this ought to be a piece of cake. You know about PSI. You can't escape from PSI. You can't do chemistry on a system if you don't know what the hell's in the system. So you always got to start with the PSI. So, as we did before, Let's go after the value for K for this equilibrium. What shall we do to proceed with this evaluation of K process? Shall we go hydronium ion over hydronium ion? Let's see what that allows us to achieve. Well, in the denominator, I've got ammonium ion, up top ammonia and hydronium ion. So up top I have that. And up top I've got hydrated CO2, and the denominator bicarb and hydronium ion, which are the products of the reaction established by hydrated CO2 reacting with water. But that is in reverse, so to speak. So K for this is Ka ammonium ion divided by Ka HCl. Now then, $64 question. From what we have so far done, is it or is it not a fair statement for this ammonium bicarb system that the molarity of this and the molarity of this are equal? Which would mean that the molarity of this and the molarity of this are equal. Is that a fair statement? Don't forget PSI. You see this reaction? Did we not consider this reaction for the sodium hydrogen carbonate solution? Do you think this reaction will also apply to the ammonium hydrogen carbonate solution? Yes or no? Yes. Is hydrogen carbonate ion a principal species in this system? Yes. Then that reaction applies, doesn't it? And what's K for that reaction? Well, we got it on the board, 1.1 times 10 to the minus 4. Now K for this reaction is 5.6 divided by 4.2 times 10 to the minus 3. Anybody got a push button grinder? Do the 5.6 divided by 4.2 for us. Come on, fast. Let's go, push those buttons.
1.33.
1.33. So take a look at 1.1 times 10 to the minus 4 and 1.33 times 10 to the minus 3. Now clearly the 1.33 times 10 to the minus 3 is the bigger number. But do we see a gross difference in the magnitudes of these numbers, the likes of which we observed for the previous systems considered? No, we don't. So what does that mean? Question, which I already asked, now we'll ask it again. For this ammonium bicarb solution, are the molarities of these species equal? No. Are the molarities of these species equal? No. How will the equilibrium molarity for this system, how will the equilibrium molarity of hydrogen carbonate ion compare to the equilibrium molarity of ammonium ion? Which one is smaller? The equilibrium molarity of? That's correct. Why? Because this reaction consumes hydrogen carbonate ion, and that reaction consumes hydrogen carbonate ion, right? So, how will the equilibrium molarity of, for this system, quote-unquote H2CO3 compared to the equilibrium molarity of ammonia? For which? The H2CO3, because we got now two sources of H2CO3 that we have to pay attention to. So guess what? Is material balance and charge balance necessary to get at this system? You're damn right. How about that? So let's write down the nuts and bolts of this, and then invite you to proceed with the analysis, because you need to practice. What are you going to write for material balance? You recognize there are two material balance considerations for this system? Will you accept that? Is material balance for all forms of ammonium ion? Because we either have ammonium ion in the system or ammonia, which is what is produced when ammonium ion loses 1H+. Because the only chemistry that ammonium ion shows us is to lose 1H+ behaving as a weak acid. What's the other material balance equation? Be careful. Don't tell me, write it. Time's up. Did you write this? Or did you forget carbonate ion? You forgot carbonate ion. Don't forget the chemistry which we have so far done. Because, have we not recognized once again with this analysis that hydrogen carbonate ion has the interesting property of behaving as an acid which is stronger than water, as well as a base that's stronger than water? How about that? Now then, what about material balance? Pardon me, charge balance. Positive ions. Ammonium ion and hydronium ion. And of course we've got to include hydronium ion since that's what we want to calculate, the hydronium ion molarity for the system. In the negative species, bicarb ion, hydroxide ion, and twice the carbonate molarity. One remaining question for this system. Can we, at this stage of the game, set this charge balance equation equal to a charge sum? I'm listening.
Yes.
It seems as if we're at odds end with each other. I hear yeses and I hear noes. Clearly one of these groups are correct and the other ain't. So we'll pick it up from this point on Wednesday.